when we heat something up at a constant power, it means that every second we put the same amount of energy in. And so long as it doesn't go through a state change, then what is going to happen is its temperature is going to rise. That every 10 seconds, for example, of this, the temperature will go up by a certain amount, 4 or 5 degrees, and then in the next 10 seconds, 4 or 5 degrees still, and then 10 seconds more, 4 or 5 degrees. The temperature rise is proportional to the time that this is on for. Now, this works, this proportionality, whenever something is being heated actively by some sort of electrical device, so an immersion heater or indeed the element in the kettle. This will change temperature in a straight line if you drew it on a graph. But now, things out there in the real world aren't always heated by a constant source of electrical power. In the real world, some things change temperature because they are different in temperature than objects around them. What I've got here is an experiment that's going to show you what happens when something that is hot and something that is cold are left to reach the ambient temperature. So first of all, I have some water here, 1 litre in fact, and I put a tiny bit of ice in it to take the temperature down, and that ice will be melted very, very soon. The temperature of this is starting out at about 0 degrees. In this second beaker, I'm going to put 1 litre of the boiling water. And so we have the same amount of water in both of these beakers. And then what I'm going to do is, I could stand here and measure it with a thermometer, but I have other things to do. So I'm going to put a temperature probe in each one. So one is ice, one is water out of the kettle, and I'm going to have the temperatures of these recorded every second or so and plotted on a graph. So I'm going to set this going, select the total recording time, not 10 seconds. I want this to record for 3 hours, and every 20 seconds it is to take a reading. And so when I press play on this, hopefully it should record the temperatures to start with. So beaker on the left is starting out at 88.1. It's already lost some of that temperature. Thermal energy has been given off somewhere, and this was already slightly above freezing when we began. But we're going to leave this now, and we're going to come back and we're going to see what happens to the temperature of these 2 beakers as we let them change temperature naturally. Now, any substance is going to have a little bit of thermal energy. The atoms in a solid, for example, can vibrate around their fixed positions. And if I was to expose this solid to another substance who had a different amount of thermal energy, then what you would find is some of the vibrations would transfer from one to the other. Say, for example, I had another one of these that was shaking rapidly right next door to this. It would transfer the vibration into this lattice structure. There would be conduction of the thermal energy. Heat would travel from one to the other until eventually they both reach the same amount of vibration. At that stage, neither this object nor the other one can gain or give any more energy than they're actually receiving. They reach something known as thermal equilibrium. Both objects have come to the same temperature. Now I have here a little experiment that demonstrates that. So what I have is a thermal imaging camera, and I have here a cube of metal, and it is in some boiling water, and then I have another cube of metal just here. Why don't you come closer and then you can see what we're doing. So we have the thermal imaging camera pointing at this cube here. It's 21.5 0.2 degrees. And we're going to put the hot cube now, which has more thermal energy, on top of, shake the water off, on top of this cube here. And we're just going to leave it there. And I'm just going to place that on the top, like that. So in that example, both blocks were the same size. They had the same number of atoms as each other. And this meant that when in contact, the amount of thermal energy that they had between them then became shared. And because they were the same material, the same mass, it meant that the temperature that they reached when they were in thermal equilibrium was exactly halfway between the temperature of the colder object and the temperature of the hotter. But what happens if you have, say, an object like this, 2 centimeters on all of its sides, comes into contact with something that is much more massive? Well, let's see. These are both iron, and this block here is being heated by a Bunsen burner, and that is 1 kilograms worth of iron. And you can see that right now it is very, very hot indeed. We want to see just how quickly this changes temperature and to what temperature when I place this small cold block on this large hot block. So the first thing I'm going to do is I'm going to turn the gas off, and we're going to take a measurement first of the temperature of this block, and the temperature of the block it thinks is 26 degrees. Then we're going to place it on here. Then we're going to watch what happens to the little block that is on top. And you can see that it is changing temperature rapidly. And very quickly is the small object gaining thermal energy from the large object. Now, the average temperature, or the temperature at which these reach when they go into thermal equilibrium, is not going to be exactly the halfway temperature between the two, because the object below is a much larger reservoir of thermal energy than the object above. It means that the object above is going to raise in temperature far more than the object below is going to drop. In fact, if I carried on with the camera filming here, the temperature would be going down in this larger block much slower than the temperature is going up in the smaller block. Now, if I had a cold larger block and a hot smaller block, we would call that a heat sink, because in that situation, the small block that was hot would lose its temperature far more rapidly in trying to gain thermal equilibrium with the larger block. And sometimes in computing we see heat sinks. Hot, small processors are attached to a big lump of metal, and they try to reach thermal equilibrium. And when they do reach thermal equilibrium, that temperature is a whole lot colder for the processor than it is warmer than for the heat sink. And so by this method, we can actively take heat away from a hot object that we don't want to be hot. So what's happening here then? Well, we had this boiling water, and we've just left it out and looked at what the temperature was doing. And the temperature is indeed falling. In the colder beaker, the temperature is rising. But why? What does it mean in terms of the particles of the water? Why is it doing this? Well, if we take, for example, the hotter of the two, its particles are vibrating with great energy. And that thermal energy is being shared with objects with which it is in contact. And you might think, well, there's no second object here. There's no block on top of another block. But what there is this water touching the environment around it. I want you to imagine that the bench, the air, the walls, all of those things that are close around the outside to this are taking some of the thermal energy from this. And so in this situation, all this hot water is trying to do is reach thermal equilibrium with the environment. Now, for that to happen, both the temperature of the environment must go up as the temperature of the water comes down, and that the final temperature of both objects, when they are in thermal equilibrium, will be well, a lot colder than the boiling water and only fractionally warmer than the environment was before. So why does the environment not warm up very much and the beaker cool down so much? Well, it's because of the difference in mass of the two objects. The environment's mass is huge. It's the entire planet. Whereas the water's mass is 1 kilogram. It means that the Earth and the environment is basically like a giant heat sink. It can take the thermal energy from this 1 kilogram of water, absorb it without appearing to even change temperature at all. But the converse is true here. The Earth has so much heat, being of higher temperature than this 0 degree water, that it can contribute that heat readily to this, heating this up to room temperature. And we don't detect any great loss of temperature in the environment because the environment is just so big. A further detail that we can see is that the rate of cooling, or the rate of heating, isn't constant. It doesn't follow those lovely straight line graphs we saw with specific heat capacity. Because remember, in those situations, we had a constant power source. We had an immersion heater heating up those substances, putting in a constant amount of energy every second. But here, it looks like the temperature is changing really fast to start with, and then less and less fast as time goes on, at a much smaller rate. Now, if the rate at which the energy is being lost appears to be changing, it must mean that, to start with, a very large amount of thermal energy was leaking away, and as time went on, less and less and less in a given time interval. This is how objects behave when they're brought or trying to get into thermal equilibrium. When the difference in temperature between object A and object B, for example, is really great, then the rate at which thermal energy can be conducted as heat is really high. But as they get closer and closer in temperature to each other, then the rate at which thermal energy conducted from A to B becomes really low. Eventually, both of these lines will converge as they become the same temperature as the room, but in this case, in many, many hours.